Hi everyone, welcome to the Operating Systems course, part of the online masters at the University of Texas at Austin. My name is Vijay Chidambaram. I'm an assistant professor at UT Austin, and today I'm going to be introducing the course and introducing who I am, talking about what you'll be learning in this course. And we'll also be learning about x86 a little bit today. So, about me, I did my undergrad in India at a university called College of Engineering, Guindy. So this is one of the oldest universities in India. So I did my undergrad there, and after that I went to Wisconsin for my master's and for my PhD. Now, interesting thing is that the place where I'm from in India, Chennai, is a very hot place. We joke that the three climates we have are hot, hotter, and hottest. There is no mild. So going from there to Wisconsin, which had it was a winter wonderland, that was a big change. Thankfully, the first year I was at Wisconsin, it was kind of like a mild winter. Mild in terms of what Wisconsin would consider mild, which is like 0 degrees, that helped me adjust. But it was a fun 6 years in Wisconsin as I did my master's and my PhD. And after that, after I graduated, I spent 1 year in VMware in sunny California. That was like dream weather. And then I spent 1 year there, had a lot of fun. And after that, I joined the University of Texas at Austin in 2016. And since then, I've been doing research on operating systems, distributed systems, storage systems, and I've been teaching graduate operating systems, virtualization, distributed systems, and so on. I have a passion for sort of teaching. I want more people to understand what operating systems are, and this is sort of my motivation for doing this online master's course. So I run this research group called the UT Systems and Storage Lab, and like I said, we research on how do you make better operating systems, how do you make better storage systems, better distributed systems, and so on. It's a fun group, and a lot of the stuff that we're learning in this online course actually maps very directly to the research that I'm doing. So if you're as you're going through this course, you find, oh, this stuff sounds interesting. What does the research in this area look like? I would encourage you to go over to my lab and check out what we're working on. All right. So the goal of this course is going to be to introduce you guys to operating systems concepts. So after taking this course, you will have a much better understanding of what goes on under the hood in Mac OS X, in Windows, in Linux, and so on. Right? You will actually be building small parts of an educational operating system called x86 from MIT as part of this course. So you will have hands-on experience in building parts of an operating system. I'll also be introducing students to research a little bit in this course. So there will be advanced topics here and there in this course where we'll be talking about this is the fundamentals, what is actually happening in the field today, what is the recent research that came out today in this particular topic. Now, I should make it clear, the goal of this course is not to prepare students for a research career in operating systems. So if you want to do that, you want to take a more advanced course which focuses much more on doing research projects, reading a lot more papers than what we're doing here. This course, I would think of it as a combination of an undergraduate operating system course and a graduate operating system course, because there are elements of both, but it's not a replacement for research-oriented graduate operating systems. Perhaps we'll do an online course for that one day. All right, so we built this course taking inspiration from two very famous and popular courses. So one is from Wisconsin, from my advisors Remzi and Andrea's undergraduate operating systems course, and from MIT, where Frans Kaashoek and others have built this wonderful operating systems engineering course. So our course takes inspiration and in some cases content from both these courses. So we wouldn't be able to do this without them, so thanks to both these groups. Now, to take this course and to do well, you will need a background in computer architecture. So when I say things like here's a register, here's a memory bus, here's a CPU, you should understand how that works. It is possible to sort of pick this up as we go along, but I would strongly encourage that you take this course after taking some undergraduate computer architecture course. You should have some experience of programming in C. because this course will involve a lot of like C programming. So if you previously only programmed, for example, in Java, a lot of the concepts here are going to be hard for you to grasp. So I would definitely encourage that you have some C experience before you take this course. So in this course, we will have a series of lectures covering OS fundamentals, like the different abstractions provided by an OS, how do different components interact, how do they all work together, and so on. And the way we'll be learning a lot of this stuff is by looking at the educational operating system called x86 from MIT. This is, it's what the MIT 6828 course is based on. It's a small educational kernel, but it will allow us to actually get a feel for like how an actual operating system works. So we'll be, by the end of this course, you will know and understand x86 a lot more. We will also be doing projects involving C and x86, and through this you will also get more experience hands-on working with different aspects of the operating system. For example, one project will be involving page tables, and by the end of that project you will know how page tables work in significant detail. When I taught the undergraduate operating systems course in Wisconsin, I found that students appreciated and enjoyed the projects the most in this course, because that's really when they have this strong intuition as to how the operating system works, when they've actually modified something in an actual operating system. So we'll have both lectures on like the fundamentals and lectures which incorporate research papers, as I mentioned before. So for example, we'll be talking about scheduler activations at some point. So that's a paper that's a little bit more advanced than the fundamentals that we talk about, but it'll give you a very good feel as to like, what does research in this area look like, what's current state of the art in this segment. So let me actually sort of like give you an overview of like how computers work. This is going to be very basic stuff that you'll need throughout the course, and later on we're going to be jumping into like how a specific architecture x86 works, and we'll wrap up the class by demoing x86, which you're going to work on throughout this course. All right, so let's actually get started, and I'm going to be sketching out a little bit on my iPad. All right, so let's just talk about the different layers that you will have in your stack. So for example, initially you will have your hardware. Okay, so this is your motherboard, your chip, the actual silicon that Intel puts out, which actually runs your computer. Okay, now a very broad way of looking at an operating system is it is the thing that sits between the hardware and the users and allows them to run application. So for example, let's say you want to run Word, right? Now the way it happens is it goes to the operating system, and the operating system then interacts with the hardware and then runs that application for you. So the operating system is sort of like the mediator in this sort of like world. Now one thing we should make clear is that like a lot of the stuff that in C programs, for example, a lot of stuff that students are typically familiar with, like for example the printf function, that's actually a user space library. So for example, the way that would actually work is you have your OS and then you have your libraries, and then on top of that you have your application. Now, so a lot of the different functions that programs call upon, like for example, when you want to write to a file or when you want to call printf, that's actually calling a library. Then the library in turn is calling the OS, and then that mediates with the hardware on behalf of all the users and all the applications. So this is back when I was doing undergrad, this always used to sort of like confuse me, because many of the things that I thought the application was interacting with the OS, it turns out that it was just a library which is then interacting with the OS, right? For example, glibc is a very popular library. So whenever you call printf, you're actually calling into glibc, which then calls into the application. So for example, a printf would be a function in glibc which would be calling write at the OS level. So all the library functions get translated into system calls at the operating system level. But let's not worry about that for now. This is just to sort of like give you a high level idea of like, like what does the stack look like, right? So your operating system is sitting closest to your hardware, and it is providing different services to applications and users. And what we're really going to learn about is like how is this operating system actually implemented, right? So moving back to our slides. So now that I've given you sort of like this high level picture of like how the layout of like the different the layers in the stack, what's the purpose of an operating system, right? So the first thing on our list is what I just talked about. We want to abstract the hardware to provide performance and flexibility. So we don't want users to be writing code directly on the hardware. So the operating system is sort of like this intermediate layer which makes it easier to do all of this, and you want to do this at high performance, right? So just because the operating system is giving you this like nice abstraction, if it's 10 times slower, people will not use the operating system. So it has to be high performance, but also has to have flexibility so that different users can run different applications on top of it. Another thing that the operating system does is that there may be multiple users on the same server or desktop, and they may be all trying to use the same hardware. And somebody has to basically mediate between all these different users and say, here, you can use the printer at this point of time, you can use this printer in the next time quantum, and so on. So the operating system is actually doing that. Another important aspect of a operating system is that just because like another user is doing something wrong, right? You don't want them to be able to bring down the whole operating system. So you want to isolate different applications so that even if one application is buggy, it doesn't bring down the whole operating system. And this is a very technically challenging thing to do, and there's been lots of research on how do you efficiently isolate different applications. And while we want to isolate applications, we still want to enable sharing between applications. So let's say there are two applications which need to share some data. Like we want the operating system to enable doing that. So a lot of like these goals are like slightly contradictory. We want to isolate, but we also want to share, for example. And so operating system design, the reason it's interesting is because of all these like contradictions. Like you want to have isolation, but you also want to have sharing, right? So that's really why it's interesting. And of course, as I mentioned before, we want to do all of this at high performance. So if your operating system is really slow, nobody will use it. And people who use Windows have some experience with this. So why do we want to study operating systems, right? So one view of it is that it's an example of like how do you actually run an application at very high performance on the hardware. So operating systems are non-trivial software artifacts, and so how do you build them such that you're able to extract the most performance that you can from the hardware is a very challenging task. So even if you don't care about all these sort of like other aspects of an operating system, just looking at it as a piece of software, it's a very interesting piece of software, and that itself is worth learning about in some sense. Another reason to study operating systems is to better understand what happens underneath the hood, and this can come handy in a number of different cases. So let's say you're building an application, and the application has very low performance. So and you're sort of like at your wit's end as to why you're getting this low performance. Oftentimes what happens is that the way it is interacting with the operating system is what is resulting in low performance. If you know more about how the operating system works, you can sort of like get better performance. Another reason is security. So if your work will involve building secure applications, it's always useful to know how the operating system underneath you is behaving, because security is end-to-end. So it doesn't matter if you have a very secure application, if the operating system is insecure and your application might be compromised because of the operating system. So it always helps to know what is going on underneath the application in the operating system layer. The OS provides a number of different abstractions, and we'll be learning about them in significant detail throughout the rest of this course. So for example, if you want to run computation, let's say you want to add, you want to subtract, computation like that, you need some sort of abstraction as to how you want to do it. And the operating system provides the abstraction of a process to enable that. To access memory, it provides abstraction of an address space. To access storage, it provides abstraction of a file. Now, all of these things are like have been in use for a really, really long time. But when you're learning them, we'll sort of like think about them like how did the design of these things come about? Why do address spaces work this way? Why do files work this way? And so on. So if we divide our course into sort of like different chunks, one chunk will be for process, one chunk will be exploring address spaces, and one chunk will be exploring files. So these are all the different things you will learn about in this course. So with that, let me sort of like talk a little bit about like why designing an OS is hard, right? So as I mentioned before, a lot of contradictory goals are in place, right? So it must be efficient, so written, for example, in a low-level language like C, but you also want it to be portable. So if you, one of the big advantages of Linux is that it will actually run on a lot of different hardware. So it will run on like the latest sort of like Mac OS X, the latest Apple computer, but it will also work on like a laptop that was like from like, let's say 2000s. So it will work on like a lot of like different ranges of hardware, and it makes very little assumptions about like what the hardware provides. So so that's sort of like a contradictory goal. If you're very low level, you're very tied to the hardware, but if you're portable, you're not tied to the hardware, and you want to achieve these things simultaneously. The operating system must be powerful, so it must be able to provide a lot of different abstractions. It must be able to provide, it must be able to allow like a lot of different applications to run, but the operating system also has to be somewhat simple. So a sort of like standard rule is that the more complex a software is, the more bugs there are in that software. So given how critical an operating system is, we don't want it to be overly complex. So we want it to be easy to reason about, easy to write, and so on. So these are like, again, contradictory goals that we somehow, operating system design has to handle. And a lot of the different features that an operating system provides are actually interact with each other. For example, if you have opened a file and then you fork that process, the child will also get a copy of that file, or will get the file descriptor. So you have to be really careful in how you design these features such that they interact properly when you write an application. So this is sort of like another reason why operating system design is hard and challenging. So, so now we're going to talk a little bit about x86. So this course is going to be built around x86, the operating system, and the x86 processor architecture. Now, there are a lot of like different processor architectures, but in this course, we're going to be focusing more or less on x86. So for this, if you look at sort of like the figure on screen, this is a Jaguar board which has a very simple x86 chip. So if you look at it here in the center, there is an Intel CPU, and then all around it, and in fact most of the board area is for your peripherals, right? So there is a socket, for example, for your flash storage. There's a HDMI port, there's a USB port, there's a network interface for a power interface, and so on and so forth. But the sort of like central square in there, that's really the Intel CPU, and that's the x86 hardware that we're going to talk about. So now I'm going to be using some slides from the MIT 68288 course, where they really sort of like very nicely lay out what the x86 architecture is about. So let me go ahead and open that up. All right. So these are slides from MIT 68288 course by Frans Kaashoek. So what we're going to be learning about is how does an x86 processor sort of look like, and how does it work. So again, to give you the context for all of this, you want your computer to be able to do something useful. And at the sort of like lower end of this, it's going to be a processor which is just which executes a series of like zeros and ones. So how do you program this processor to do anything useful is what we're going to talk about, right? And again, there are a number of different processor architectures, x86, ARM, etc. And in this particular course, we're going to be focusing on x86. And what does it actually mean when I say we're going to be focusing on x86? So the x86 processor architecture has a specific set of instructions. So if you have an x86 processor and if you have an ARM processor, they will take different instructions. So the same series of like zeros and ones sent to these two different processors will mean different things to each processor, right? And so we're not going to worry about like how ARM interprets zeros and ones. We're going to worry about how x86 interprets zeros and ones. Okay. So again, like another picture of like an x86 board, and broadly, right? Like this is the way to sort of like think about this. So you have a central processing unit, in other words, a CPU, which is actually doing all your computation for you, right? And it's going to take input and output. So you have, for example, a file on storage and so on and so forth, and then it's going to be processed by this central memory, central processing unit. Now it's going to actually use main memory, your DRAM, your dynamic random access memory, to actually keep the stuff that it is working on, right? So the way you should think about sort of like a program in this x86 architecture is it's a sequence of instructions which operate on data. And these are all instructions that an x86 processor understands. So for example, let's say the x86 processor understood only adds, then all your programs are going to be a sequence of like add instructions with different arguments. For example, add 1 plus 2, add 2 plus 3, and so on, right? Now, x86 actually takes a reasonable amount of like instructions, so your programs are going to look complex, but at the core, they are just a sequence of instructions operating on data, right? And all your CPU is going to do is, in an endless loop, right? It's going to just take the next instruction, it's going to figure out what the instruction is, and then it's going to execute that instruction. That's really what your CPU is doing. Now, I'm not providing a lot of detail on like how this actually works. So if you took an undergraduate operating system course, you will know, for example, stuff like there's going to be prefetching, there's going to be parallel loads and all of that stuff. But for the purposes of this course, right, you don't have to understand the internals of how a CPU works. The model that it's a loop executing instructions is enough for us. Okay. All right. So now, if you have a bunch of instructions in memory, how do you know which instruction to sort of like execute next? So the x86 processor keeps track of it with what is called the instruction pointer. Okay, and hopefully you understand what a register is. Registers are like really low latency memory, bits of memory that is stored on the alongside your processor. So it's a small amount of like very fast limited memory that your processor can access. So we call this a set of registers, right? So you have a certain number of like registers that your processor can access at high speed. So one of these registers is called EIP, the extended instruction pointer, right? So the instruction pointer will keep track of like which instruction to next execute. So every time you execute an instruction, the instruction pointer is going to be incremented. right? And every time you do call, which means you're calling a different function, or you're returning from a function, or you're jumping to a different point in the code, for example, using goto, these things all change the instruction pointer, right? Okay, as I mentioned, your registers are really your fast, high-speed memory addresses that you can use while you're writing your program. So the way to think about them is like this very fast workspace. So you have, let's say, a few registers where if you read and write from them, it's going to be really, really fast. But you have a very small set of these registers, so you have to be careful in how you use these registers, right? And when you're, for example, in this particular instruction, we have add EAX 10. So what that particular instruction means is add whatever is in register EAX with 10. So that's what that particular instruction means. You have other instructions like subtract and so on and so forth. So there's a bunch of different registers, but in this particular course, you don't have to go into a lot of detail, but it is helpful if you understand this is how the hardware is actually executing different things, right? So as I mentioned before, your set of registers is tiny, right? You have a handful of registers that you can work with, but of course, the stuff that you want to work on sometimes is bigger than a handful of registers. So what happens then? That's when you use DRAM, your main memory, right? That's slightly slower, or compared to registers, significantly slower, but gives you a bigger working space. So for example, a way to think about this is like, let's say you're working at your desk and you can keep a small set of items with you on that desk. So those are your registers. But sometimes you need to work on something different, so you go to, let's say, your closet and you fetch stuff. So your closet is basically your main memory. So in this example, like reaching for something on your desk is very quick, but then going to your closet and getting stuff is very slow. And that's the same setup with registers and DRAM as well. So if you want to go to main memory and you want to actually fetch something that's significantly slower than just accessing something that's in your register. So the consequence of what I just described is that you want to be very careful in how you use your registers. So if possible, you want to read and write just from registers. But you have to be careful because you have limited amount of registers. And if you think about like how do we actually manage this, this is one of the things that a compiler does for you. So in a modern programming language, well, or a high-level programming language like C, you don't actually manipulate the registers yourself. You just say, add this number, print this number, and so on. And what the compiler will do is, underneath the covers, it will transform them such that you are going to main memory as little as possible, right? And this is something that's just like interesting for you to know, because like if the working set of your application fits entirely within a set of registers, that is going to be dramatically faster, let's say 100 times faster than going to actually main memory and fetching stuff from main memory. So just something for you to know about. Now, back to our slide. What we're seeing here is that there are different ways in which you can access your registers and you can access memory. So first, when you look at this, right, so it says you're going to be doing movl, EAX, EDX. This is, you're manipulating two registers. So you're saying whatever is in EDX is going to be whatever is in EAX. So this is going to be a very, very fast instruction, right? Another thing you're doing is you're going to say move whatever, you move value 123 into register EDX. This is again going to be extremely fast. The next step becomes significantly slower, right? Now what you're saying is whatever is in address 123, you're going to load that into EDX. So this is not a register. So this is main memory. So your application has to go from CPU to main memory, fetch whatever is in address 123, and then use that and put it into EDX. So there's a bunch of stuff that I'm not talking about here, which is like your processor has multiple levels of caches. So oftentimes it's not going to be that you're going to be reading this from memory, but your processor is going to be smart enough to know, oh, look at this, like our programmer wants to read 123 soon. So let's go ahead and fetch 123 from main memory into our caches before actually the instruction gets executed, so that when you execute this instruction, it's much faster. So a bunch of like very neat tricks that computer architects play to make our programs faster. Continuing on with the slide, there are a bunch of different modes that you can execute to use to execute instructions. So you can use direct mode, where you're saying it's going to be the value in address 123. You can also use, say, whatever is the value in EBX, let's say 124, if you use that as a memory address, go to 124 and fetch whatever is in 124 and put that in EDX. So this is indirect mode. It's using the value in EBX as an address and then seeing what's in that address and then putting it in EDX. So if you're familiar with like pointers in C, this is really what is going on here. And finally, you also have relative displaced mode. So for example, you could say EBX is like 124. Add 4 to 124 or whatever is in EBX and fetch the address from there. And this is useful because like a lot of like stuff that we do is relative. Like we won't be dealing with like absolute addresses, but rather with relative addresses a lot in our programs. So if all of this is like very overwhelming for you, like don't worry about it. You don't need to be like a hardcore assembly hacker to take this course. I'm explaining all of this so that you have a reasonable understanding of like what assembly looks like and what actually goes on underneath the hoods. But for the purpose of this course, all you really need to be able to do is to read assembly somewhat, so that like at certain points in the code, when you have to move to registers, you can do that. But you wouldn't have to write like really long programs in assembly. That's not going to be required for this course. All right, so another thing that we should sort of like understand is what a stack is. So let me actually like wait. Actually, like I think I have. Yes. Okay. So let's go to this slide and we'll come back to that slide later. So if you look at this slide, like what it's showing is that like how do you actually use the memory of your device. So in this particular case, there's 4 gigs of memory, and then like how do you actually use it is what this figure is showing you. Now, if you look at it, there's the slot of stuff like, for example, your VGA display for your number of devices, your BIOS, and then there's extended memory, and then you have a bunch of stuff, right? So in this particular picture is where your stack would be for your program. So let me actually switch to the iPad, and I will actually draw out like what a stack looks like. Okay, so let's see. Okay, so first of all, what is a stack and why do we need it? When we are programming with C, there are different kinds of like operations we want to do. So right. So for example, so you have, let's say, main, and then from main you're going to call foo. Let's say this is sort of like what your program is doing. So every time, from sort of like the architectural level, we have to keep track of like what function is executing and what is within scope for that function. So for example, let's say you had x in main, which is 20. And then you have another x in foo, which is 10. So when you're executing foo, if you're trying to access x, it should give you 10 and not 20. So you need to be able to sort of like figure out like which function is executing and what is the context for this function. And the context for a function is basically all the variables that it's accessing, the arguments that are given to the function, and so on and so forth. So all this stuff, the sort of like temporary stuff that every function has, that lives in the stack, right? And every time you call, so let's imagine a stack looking like this. And so initially you had main, and then you had all the context for main in that stack. And then when you call foo, all the context for foo is within that frame in the stack. So every time you call a function, you keep adding layers to the stack, and every time you finish a function, you pop a layer of the stack and you go back to the previous state. And so because like you only when you're executing, you're only executing one function at a time, and you only care about the context of that particular function, a stack is a very appropriate data structure to use for this. So whatever is the current layer that we are at, those are the variables that we care about, and that's what we are accessing. All right, so that's what's called a stack. Now, somewhat weirdly and confusingly, the stack grows downwards in x86. So the stack starts off here. So in our example, let's say the stack starts off at address 1000, right? So main will be at address 1000, and then foo will be at a lower address. So let's say the stack frame is like 100 bytes, just in our example. So foo will be in 900. Now this can be the source of a lot of confusion because like the stack grows higher is what they'll say, and what is actually going is that it's going lower. So this is something important that we want to sort of like remember, that stack always grows downwards. So the more recent function that you have on your stack will have a lower memory address than the first frame in your stack, which will have a higher memory address. So the reason they do this is because they have only one address space, and there's other stuff that they want to put at the bottom. For example, the instructions that comprise the program, the global variables in your program, and stuff like that. So they want to put a certain amount of stuff here, and then they want to start the stack here, and then they just want to keep growing it downwards until it hits the other stuff that you have put in your address space. So just because we don't know how big the stack has to be, as you call more functions, you'll be using up more stack space. They just started at the other end, and then they just grow it downwards. But this could be a source of a lot of confusion. So this is something I want folks to remember as we sort of like go through the picture. So to sort of like summarize that again, as you execute different functions in your C program, the context for those functions is going to be in your stack. It's a data structure that grows every time you call a function, and reduces in size every time you return from a function. And in your process address space, it starts off at the top and then grows down to the bottom. So if you have a lot of like functions, that's going to be using smaller and smaller addresses as you go down the stack. Okay, so this is something that we want to keep in mind. So let's sort of like move back to our slides where there will be like more detail on like how the stack works. So if we look at our slide, we can see that like here's like something that is being pushed onto the stack. The EX register is being pushed onto the stack, and interestingly, the way that is implemented is it is subtracting 4. Okay, so sorry, I didn't explain what this is. So because the stack keeps moving, you have to have some way of knowing where the current end of the stack is. Remember that we had the instruction pointer to track which is the next instruction to execute. Similar to that, we have the stack pointer, extended stack pointer, or ESP, to track where the end of the stack is. So that's what the ESP means. And when you start the program, ESP is going to be the top of your address space or your memory, and then it will grow downwards. So when you want to push something to the stack, they are subtracting 4 because that's the size of the EX register from your sorry, I was mistaken. That's not the size of the EX register. That's the size of the stack frame. So every time you'll be moving the stack pointer, you'll be subtracting 4. So so here you are subtracting 4. And then you're moving EAX onto the stack pointer. So this instruction if you're able to pass it, says take EAX and then put it where ESP points. So wherever the stack, the top of the stack was. And so when you pop the stack, let's say you're done with your function, you want to pop the stack, what is happening is that you are moving your whatever was the at the stack pointer into EAX, which is the return value, right? So every time you call a function and then you're expected to return some value number, that number or like whatever your return value is will be in EAX. That's the register for it. And so you're moving that value into EAX and then it's adding 4 to the stack. So the stack is growing, it's going to higher memory addresses, which means it's becoming smaller. I know this is really confusing, but an easy way to remember this is in a world where you didn't have like an upside down stack, all of this would be reverse. When you pop a stack, you'd be subtracting. When you push a stack, you'd be adding. But because the stack goes downwards, it's the exact reverse. When you pop a stack, you're adding. When you're pushing onto a stack, you're subtracting, right? And when you're calling a particular function, what is happening is that you are again like you have your instruction pointer and you're using it to move to that address. We're using this to implement functions, right? We have segment registers and stuff. We don't need to talk about that right now. All right. One thing I want to emphasize as we sort of like go through this is that when you're using GCC to compile your C programs, it uses the calling convention that we just talked about, where you're going to be pushing stuff on your stack as you call a different function. So in this particular slide that we're looking at, when we are calling a function, what we're seeing is that, remember how I told you everything that's in context for a function is going to be inside your stack. So a register called EBP, the extended base pointer, is actually the context for your particular stack frame. So a different way to sort of explain that is to say, when you have like let's say argument 1 and argument 2, the way you're going to reference to that is you're going to say that's going to be 2 entries above my stack pointer, right? But your stack pointer is going to be keeping moving as you call functions here and there. So because of that, what you do is you use a base pointer to solidify the start of your current context for your function. So EBP is not going to change. So when you say 2 entries on top of EBP, that's going to be the same thing. So that's what EBP is sort of like used for as you go through your different functions. Okay. So again, this is just something to know, and you'll get used to this as you go through this course. Your EAX register contains the return value. There are some registers that your function may use and may change, but there are other registers that must be restored before you return from the call. Your base pointer, EBX, ESI, and so on. Okay. Again, you don't need to know a lot of this detail, but occasionally we might want to look at assembly code in the class, and when we're doing that, I want you to understand like what's going on. So that this is all this overview, so that at some later point of time when you're looking at assembly code, you're able to understand what is going on. Okay, so this is an example of like how different functions in C are getting translated into different into assembly code. So there are 3 functions. There's main, there's f, and there's g, and what we're looking at is the assembly code that's generated for all of these things. So the first thing I want you to note is that every function has a prologue and an epilogue. What that means is whenever you are inside a function, you have to save certain registers, so that even if your function is overwrites those registers, when you're exiting from that function, you're able to return to the correct value. So for example, your base pointer, your EBP, is something that's really important. This is basically the code that was executing before you call this function. So you take your EBP and then you put it onto the stack. Right, so basically push L will push your base register onto the stack. After that, what you're saying is, now I'm going to be executing in the context of this particular function. So I'll take my stack pointer, which is the start of this function, and I'm moving it into this base pointer. And so what we're seeing here is that this is prologue and epilogue that happens for every function, right? And inside this function, you have stuff like, for example, push 8 onto this stack. And why do we do that? Because we're going to call f, and the argument for f is 8, right? Then we're going to call f, and then it's going to find 8 on the stack as the argument for its function. Once it returns, the return value will be in EAX. So what are we doing? We are going to add 1 to EAX. We don't have to do anything else because EAX is the return value that we ourselves will be using. So the return value from int is also going to be in EAX. Again, don't worry if this stuff is overwhelming at this point. You don't really need to know a lot of assembly code. You just need to be able to read assembly code like this at certain points in the course, right? So as long as you take a look, spend some time and take a look at like different assembly courses, assembly language programs, you should be totally fine, right? So one other thing I want to show is the pipeline as to how an application gets built. So initially you write your C files, and then your C files are going to be executed or compiled by your GCC compiler into assembly code. Your assembly code is just then taken by the GCC assembler, and then that generates your .o files. These .o files are then being loaded, and this is because like the different files which comprise a single program, it creates an executable, in this case a.out. Your loader then takes a.out and puts it into memory, and then it's by setting things like the instruction pointer, that's how it's telling the processor this is what you should execute. So these are the different stages that a compiler and assembler and so on do to get you the final executable for memory. Alright, so in this course we are going to be using something called QEMU. Now I remember that I said that we are going to be developing our own operating system. If you run your own sort of like development operating system on your hardware directly, if you make a mistake, there's no coming back. Like your computer will not boot, right? So how do we sort of like get around this? So we use something called an emulator. So QEMU will emulate x86 hardware for you, on top of which we're going to run our x86 operating system. So it's kind of like having your own virtual small computer on top of which you're going to run the operating system that you write, and if you make a mistake, you can just reboot your virtual computer pretty quickly, and that's what we're going to be using QEMU for. Now QEMU internally will be emulating memory. So for example, you'll have a large array of memory in which if you're going to write something to address 123, there's a spot in the array where you'll be writing 123. So your entire memory is emulated by QEMU. It's going to emulate a CPU, and this is very simple. In a loop, it's just going to take the next instruction pointed to by your instruction pointer. It's going to decode that, and then it's going to run that. It's going to emulate memory also, as we just talked about. So in summary, we'll be using QEMU and x86 as we go along this course. It's important for you to understand how computers work and how x86 works at a high level. As we go through this course, we'll be developing different operating system constructs on x86. So next class, we'll be learning more about how x86 works and including a demo. So I'll see you then. Thank you.